National Electrical Code, or NEC, does indirectly require a Supplemental Direct Grounding Path, or SDS, for certain generator installations. NEC Article 250.30 A5 states that with a grounding electrode conductor is connected to an equipment grounding conductor for a generator set, it shall be connected to the neutral point of the generator. This requirement ensures that the generator's neutral is grounded, which is necessary for the proper functioning of the SDS. NEC Article 702.5 B further states that the grounding of normally non-current carrying conductive enclosures of generators and the grounding of normally non-current carrying conductive enclosures of associated auxiliary equipment connected to the generator shall be in accordance with 250.30. This requirement applies to generators that do not have a grounded neutral. In such cases, SDS is necessary to provide a grounding path for the generator's enclosure and associated equipment. Additional codes that indirectly require SDS are outlined in Article 250.30 A2, which requires that all neutral conductors be grounded at the source. Article 702.10 requires that all generators have a grounding electrode conductor connected to the generator's neutral point, and Article 702.10 D requires that the grounding electrode conductor be sized according to Table 250.122. In summary, while the NEC does not explicitly require a SDS, it does indirectly require one for certain generator installations by mandating the grounding of the generator's neutral and associated equipment. These requirements ensure the proper functioning of the SDS and the safety of the installation. Let's delve deeper into these NEC articles to understand the specific requirements and how they relate to generator installations. Firstly, let's examine NEC Article 250.30 A5 in more detail. This article specifically addresses the connection of the grounding electrode conductor to the equipment grounding conductor for a generator set. The key takeaway here is that this connection must be made at the neutral point of the generator. This is crucial because it establishes a direct path to ground for any fault currents that may occur within the generator or its connected equipment. By grounding the neutral point, we ensure that the voltage potential between the neutral and ground is minimized, which helps to prevent electrical shock hazards. Furthermore, this grounding connection facilitates the proper operation of overcurrent protective devices, such as circuit breakers and fuses, which are designed to interrupt the circuit in the event of a fault. Now, let's move on to NEC Article 702.5 B, which focuses on the grounding of normally non-current carrying conductive enclosures of generators and associated auxiliary equipment. This article states that the grounding of these enclosures must be done in accordance with 250.30. This is particularly important for generators that do not have a grounded neutral. In such cases, a SDS is necessary to provide a grounding path for the generator's enclosure and associated equipment. Without a proper grounding path, any fault currents that may occur on the enclosure could create a dangerous shock hazard. The SDS provides a low impedance path for these fault currents to flow back to the source, which allows the overcurrent protective devices to quickly and safely interrupt the circuit. It's important to note that the size and type of grounding conductors used for the SDS must be carefully selected to ensure that they can adequately handle the expected fault currents. Now let's consider the additional codes that indirectly require a SDS. NEC Article 250.30 A2 mandates that all neutral conductors be grounded at the source. This requirement is fundamental to electrical safety as it establishes a common reference point for the electrical system. By grounding the neutral conductor, we ensure that the voltage potential between the neutral and ground is minimized, which helps to prevent electrical shock hazards. Furthermore, this grounding connection facilitates the proper operation of overcurrent protective devices. NEC Article 702.10 requires that all generators have a grounding electrode conductor connected to the generator's neutral point. This requirement is similar to the one outlined in 250.30 A5, but it specifically applies to generators. The purpose of this requirement is to ensure that the generator's neutral is properly grounded, which is essential for the safe and reliable operation of the generator. The grounding electrode conductor must be sized according to Table 250.122, as specified in NEC Article 702.10. Table 250.122 provides guidance on the appropriate size of grounding electrode conductors based on the size of the ungrounded conductors in the circuit. It's crucial to select the correct size grounding electrode conductor to ensure that it can adequately handle the expected fault currents. Now let's discuss some practical considerations for implementing SDS in generator installations. Firstly, it's important to carefully assess the specific requirements of the installation to determine whether SDS is necessary. Factors to consider include the type of generator, the presence of a grounded neutral, and the potential for fault currents. Secondly, the SDS must be properly designed and installed in accordance with the NEC. This includes selecting the appropriate size and type of grounding conductors, ensuring that all connections are made securely, and verifying the impedance of the grounding path. Thirdly, regular inspections and maintenance should be performed to ensure that the SDS remains in good working condition. This includes checking for corrosion, loose connections, and any other signs of damage. In summary, while the NEC does not explicitly require SDS, it does indirectly require one for certain generator installations by mandating the grounding of the generator's neutral and associated equipment. These requirements ensure the proper functioning of the SDS and the safety of the installation. By understanding the relevant NEC articles and following best practices for design and installation, we can help to prevent electrical shock hazards and ensure the safe and reliable operation of generator systems. Let's further elaborate on the importance of grounding and bonding in electrical systems, particularly in the context of generators and SDS. Grounding refers to the connection of electrical equipment and systems to the earth, which provides a common reference point and a path for fault currents to flow back to the source. Bonding, on the other hand, refers to the connection of non-current carrying metal parts of an electrical system to create a low impedance path for fault currents. Both grounding and bonding are essential for electrical safety, as they help to prevent electrical shock hazards and ensure the proper operation of overcurrent protective devices. In generator installations, grounding is particularly important because generators are often used as a backup power source during power outages. This means that the generator must be able to provide a reliable and safe source of power, even when the normal power grid is not available. The SDS plays a crucial role in ensuring the safety and reliability of generator systems. By providing a direct path to ground for fault currents, the SDS helps to prevent electrical shock hazards and ensures that overcurrent protective devices can quickly and safely interrupt the circuit in the event of a fault. It's important to note that the effectiveness of the SDS depends on several factors, including the size and type of grounding conductors, the quality of the connections, and the impedance of the grounding path. Therefore, it's essential to carefully design and install the SDS in accordance with the NEC and industry best practices. In addition to the NEC requirements discussed earlier, there are other codes and standards that may be relevant to generator installations and SDS. These include the National Fire Protection Association, or NFPA, 70E Standard for Electrical Safety in the Workplace, and the Institute of Electrical and Electronics Engineers, or IEE, standards for grounding and bonding. It's important to be familiar with these codes and standards to ensure that generator installations are designed, installed, and maintained in a safe and compliant manner. Now let's discuss some common misconceptions about grounding and bonding in electrical systems. One common misconception is that grounding and bonding are the same thing. As mentioned earlier, grounding refers to the connection of electrical equipment and systems to the earth, while bonding refers to the connection of non-current carrying metal parts of an electrical system. While both grounding and bonding are important for electrical safety, they serve different purposes. Another common misconception is that grounding is only necessary for safety. While grounding is essential for safety, it also plays a role in the proper operation of electrical equipment and systems. For example, grounding can help to reduce electrical noise and interference, which can improve the performance of sensitive electronic equipment. A third common misconception is that any grounding conductor will work. The size and type of grounding conductor must be carefully selected to ensure that it can adequately handle the expected fault currents. Using an undersized or inadequate grounding conductor can compromise the effectiveness of the grounding system and increase the risk of electrical shock hazards. In conclusion, understanding the NEC requirements for SDS in generator installations is crucial for ensuring electrical safety and the reliable operation of these systems. By following best practices for design, installation, and maintenance, we can help to prevent electrical shock hazards and protect people and property from the dangers of electricity. Let's expand on the practical implications of these code requirements, particularly focusing on the selection and installation of the grounding electrode conductor and the importance of low-impedance grounding paths. The grounding electrode conductor, as specified in NEC Article 702.10 D and Table 250.122, is the critical link between the generator's neutral point and the grounding electrode system, which typically consists of ground rods, ground plates, or underground metallic water pipes. The size of this conductor is directly related to the size of the generator's conductors, reflecting the need to handle potential fault currents effectively. A larger generator, with higher amperage capacity, necessitates a larger grounding electrode conductor. When selecting the grounding electrode conductor, it's not just about meeting the minimum size requirements of Table 250.122. Consideration should also include the material of the conductor, typically copper or aluminum, and its insulation rating. Copper is generally preferred for its superior conductivity and resistance to corrosion, but aluminum can be a cost-effective alternative in certain applications. The insulation rating of the conductor must be appropriate for the environment in which it is installed, considering factors like moisture, temperature, and exposure to chemicals. Installation of the grounding electrode conductor is equally important. The conductor must be installed in a manner that minimizes the risk of damage or corrosion. Direct burial of the conductor is permitted, but it must be protected from physical damage, such as from digging or construction activities. The conductor should be routed in a way that avoids sharp bends or kinks, which can increase its impedance and reduce its effectiveness. Connections to the grounding electrode system must be made using approved connectors and methods. These connections should be mechanically secure and electrically sound to ensure a low resistance path to ground. Regular inspection of these connections is essential to identify and correct any signs of corrosion or loosening. The concept of low impedance grounding paths is fundamental to the proper operation of the SDS. Impedance is the total opposition to current flow in an alternating current circuit, and it includes both resistance and reactance. A high impedance grounding path can impede the flow of fault currents, delaying the operation of overcurrent protective devices and increasing the risk of electrical shock hazards. To achieve a low impedance grounding path, several factors must be considered. Firstly, the length of the grounding conductors should be minimized. Longer conductors have higher impedance, so it's important to keep the grounding conductors as short and direct as possible. Secondly, the size of the grounding conductors should be adequate for the expected fault currents. Undersized conductors can have excessive impedance, limiting their ability to carry fault currents effectively. Thirdly, all connections in the grounding path must be clean, tight, and free of corrosion. Loose or corroded connections can significantly increase the impedance of the grounding path. Fourthly, the grounding electrode system must be properly installed and maintained. The grounding electrodes must be in good contact with the earth to provide a low resistance path to ground. Regular testing of the grounding electrode system is recommended to verify its effectiveness. In addition to these factors, the overall design of the electrical system can also impact the impedance of the grounding path. For example, using separate equipment grounding conductors for each circuit can help to reduce impedance compared to sharing a common grounding conductor. Also, using metal conduit or cable trays as equipment grounding conductors can provide a low impedance path, but it's important to ensure that the conduit or cable trays are properly bonded together. Let's address the specific scenario of generators that do not have a grounded neutral and the implications for SDS requirements. In these generators, a grounding transformer, also known as a zigzag transformer, is often used to create a neutral point for grounding purposes. The grounding transformer provides a low impedance path for ground fault currents, allowing overcurrent protective devices to operate correctly. When using a grounding transformer, it's important to ensure that it is properly sized for the generator and the connected load. The transformer must be capable of carrying the expected ground fault currents without overheating or saturating. The grounding transformer should be installed as close as possible to the generator to minimize the length of the grounding conductors. The grounding electrode conductor from the grounding transformer should be connected to the grounding electrode system in accordance with the NEC. In some cases, a separately derived system, or SDS, may be required for generators that do not have a grounded neutral. A SDS is an electrical system that is powered by a source that is not directly connected to the utility grid. SDS are commonly used in emergency power systems, such as those powered by generators. When SDS is used, it must be grounded in accordance with the NEC. This typically involves connecting the neutral point of the SDS to a grounding electrode system. The grounding electrode system for SDS must be separate from the grounding electrode system for the main electrical service. This is to prevent circulating currents between the two systems. The NEC provides specific requirements for grounding SDS, including the size and type of grounding conductors, the location of the grounding electrode, and the methods for bonding the non-current carrying metal parts of the system. These requirements are designed to ensure that the SDS is properly grounded and protected from fault currents. In conclusion, the NEC indirect requirements for a supplemental direct grounding path in generator installations are essential for electrical safety. Understanding these requirements, along with the principles of grounding and bonding, is crucial for anyone involved in the design, installation, or maintenance of generator systems. By following best practices and adhering to the NEC, we can help to prevent electrical shock hazards and ensure the safe and reliable operation of these important systems. To further illustrate the importance of SDS and proper grounding in generator installations, let's consider our hypothetical scenario. Imagine a hospital that relies on a generator for backup power during power outages. The generator is used to power critical medical equipment, such as life support systems and operating room equipment. If the generator is not properly grounded, a fault current could occur on the generator's enclosure. This fault current could create a dangerous shock hazard for anyone who comes into contact with the enclosure. In addition, the fault current could interfere with the operation of the critical medical equipment, potentially endangering the lives of patients. However, if the generator is properly grounded with SDS, the fault current would be safely conducted back to the source, tripping a circuit breaker and disconnecting the generator from the electrical system. This would prevent the shock hazard and protect the critical medical equipment from damage. This scenario highlights the critical role that SDS and proper grounding play in ensuring the safety and reliability of generator systems, especially in critical applications such as hospitals. It's important to remember that electrical safety is not just about meeting the minimum requirements of the NEC. It's about understanding the principles of electricity and taking proactive steps to prevent hazards. By investing in proper grounding and bonding, we can help to create a safer electrical environment for everyone. Let's examine the role of the authority having jurisdiction, or OJ, in enforcing the NEC requirements for SDS and generator installations. The AHJ is the organization, office, or individual responsible for enforcing the requirements of a code or standard, or for approving equipment, materials, an installation, or a procedure. The AHJ can be a federal, state, local, or other regional department or individual such as a fire marshal, building official, electrical inspector, or others having statutory authority. The AHJ has the authority to interpret the NEC and to make decisions about whether an installation complies with the code. The AHJ may also have the authority to require additional safety measures beyond what is specified in the NEC. In the context of generator installations and SDS, the AHJ plays a crucial role in ensuring that the installation is safe and compliant. The AHJ may inspect the installation to verify that it meets the requirements of the NEC. The AHJ may also require documentation, such as drawings and calculations, to demonstrate compliance with the code. If the AHJ finds that an installation does not comply with the NEC, it may issue a notice of violation and require the installer to correct the deficiencies. In some cases, the AHJ may even have the authority to shut down the installation until it is brought into compliance. It's important to work closely with the AHJ throughout the design, installation, and inspection process to ensure that the installation meets the requirements. This can help to avoid costly delays and ensure that the installation is safe and compliant. In addition to the AHJ, there may be other organizations or individuals involved in the oversight of generator installations. For example, insurance companies may have their own requirements for generator installations. Also, some facilities may have internal safety committees that review and approve generator installations. It's important to be aware of all the applicable requirements and to work with all the relevant stakeholders to ensure that the installation is safe and compliant. Finally, let's emphasize the importance of ongoing education and training in the field of electrical safety. The NEC is a complex and ever-evolving document, and it's important to stay up to date on the latest requirements. There are many resources available for electrical professionals who want to improve their knowledge and skills. These include courses offered by trade schools, community colleges, and professional organizations. Also, there are many online resources, such as websites, blogs, and forums, that provide valuable information on electrical safety. By investing in ongoing education and training, electrical professionals can help to ensure that they are providing the highest level of safety for themselves and for the public. In closing, the NEC indirect requirements for supplemental direct grounding path in generator installations are essential for electrical safety. Understanding these requirements, along with the principles of grounding and bonding, is crucial for anyone involved in the design, installation, or maintenance of generator systems. By following best practices, working with the AHJ, and investing in ongoing education and training, we can help to prevent electrical shock hazards and ensure the safe and reliable operation of these important systems.